name is Thanom and I'm from the University of New South Wales. Today I'm going to be working through the questions in one of the previous class tests for Calculus MATH1011, and this one in particular is the Semester2 2008 version 1A. So question 1 is asking us to sketch x squared, y equals x squared plus x minus 6. One of the first things you need to notice is that's a parabola because it's a quadratic, it's got x squareds in it. So we're sketching this parabola. In particular, we need to show where it cuts the x-axis. That will be very important when we need to solve this inequality over here. But we might label some more features just for practice. So y equals x squared plus x minus 6. There's lots of ways to sketch parabolas. If you can factorize it though, it's very useful and it's very easy to find x intercepts once it's factorized. So if I was going to factorize this quadratic, I would be finding two numbers that multiply to give minus 6 and add to the coefficient of x, which is 1. So two numbers that multiply to minus 6 and add to plus 1 are minus 2 and plus 3. So this quadratic here factorizes to x minus 2, x plus 3. Okay, so this is a parabola. Now, we're going to sketch this. I'll try and draw some straight lines here. To find where the curve cuts the x-axis, so they're the x-intercepts, we essentially need to solve y equals 0, because here's our y-axis. Y equals 0 is where it's going to cut the x-axis here. So if we solve y equals 0, we're solving x minus 2 times x plus 3 is equal to 0. So if two things multiply to give 0, then either the x minus 2 is 0 or the x plus 3 is 0, which means x is 2 or x is minus 3. Once you practice these lots, you can read them off here and you don't need to do so much working. They're going to be our x-intercepts at 2 and at minus 3. Okay, now it's a parabola. And actually it's positive 1x squared, and so we actually know it's concave up like this, but it would be nice to label a y-intercept. To find y-intercepts, you make x equal to 0. Now that's particularly easy because if we work out 0 squared plus 0 minus 6, then that's just going to give us minus 6. So our y-intercept is actually minus 6. So I'll put that here. Now be careful, minus 6 is the y-intercept, but that's not necessarily the vertex of the parabola. The vertex of the parabola is halfway between 2 and minus 3. So the vertex is actually slightly off here at minus a half. Right? So you shouldn't draw it so that the bottom point is at minus 6. The bottom point is slightly left of that. And so our parabola going to look like this. And if we wanted to calculate that bottom point, the vertex, let's do it for practice. The vertex, well, it occurs halfway between 2 and minus 3, so we can add them together and divide by 2. That's how I got the minus a half. So the vertex occurs when x is minus a half. If we want to work out what y is, we're going to plug minus a half into either of these equations. We'll give you the correct answer. So we could do minus a half squared plus minus a half minus 6. That's a quarter minus a half is minus a quarter. Minus 6 is minus 6 and a quarter. Okay, so this point down here, it actually drops to minus 6 and a quarter. So you can see it goes slightly below where that y-intercept is. So we've sketched that parabola, and in particular we've shown where it cuts the x-axis, but moreover we've shown the y-intercept and the vertex, which generally you should show if you're sketching your parabola. Now we're asked to solve this inequality. Now, You might just have to solve it up here. There'll be enough room. Because what this is asking us to do, this is the parabola, the y value of the parabola. So we're trying to find when x squared plus x minus 6 is greater or equal to 0. We're trying to find when y is greater or equal to 0. So when is the y value of our parabola greater or equal to 0? Well, that's easy enough to see from our graph. The y value of our parabola is greater or equal to 0 when it's above the axis here. Right? So here and here is where the y value is greater than 0. Well, that's for all the x's bigger than 2 and less than minus 3. Right? So this is x is bigger than 2 and for x less than minus 3. Actually, bigger or equal to 2 and less than or equal to minus 3. Okay, so let's write that as a solution. Just over on the side here. So x squared plus x minus 6 is greater or equal to 0 when x is less than or equal to minus 3 or x is bigger or equal to 2. That's from the graph. Now, we can write that using some set notation. So if x is less than minus 3, that means x is in this interval from minus infinity up to minus 3 and including minus 3, which means we've got a square bracket there. So x could be in this interval, or, which means it's a union, it could be in the interval from 2 to infinity. So including 2 means we've got a square bracket at 2, all the way to infinity. Infinity always comes with a round bracket. So we can write our answer saying x is in this interval from minus infinity up to and including minus 3 and from 2, including 2, up to infinity. So we can write our answer like this. And that's how we sketch a parabola and use our sketch to solve an inequality over here. Question 2 is asking for another sketch, but this time of the graph y equals x minus 1 on x plus 1. Now, this is quite tricky to decipher. It's actually a hyperbola, but it doesn't necessarily look like a hyperbola because you're used to hyperbolas being a number like 1 over x plus 1 or 2 over x plus 1, not x minus 1 over x plus 1. Turns out it is a hyperbola, and we'll see why in a minute. But if we were going to sketch this, let's just work through all the different features that we would put on our sketch, try to put it together, and then we'll see why it's going to be a hyperbola. So, the different features we might want to put on this graph are, for example, the y-intercept and the x-intercept. Sometimes graphs don't have these and they don't exist, but we should try and find them if they do exist. To find a y-intercept, we make x equal to 0. So y will be 0 minus 1 on 0 plus 1. That will be minus 1 divided by 1, which is minus 1. So our graph cuts the y-axis at minus 1. To find our x-intercept, we set y equal to 0. So here we'll be solving x minus 1 on x plus 1 equals 0. Now if two numbers divide to give 0, the only way that can happen is if the numerator, the top, is going to be 0. So if x minus 1 on x plus 1 is 0, then x minus 1 is 0. Which means x has got to equal 1. Okay, so we have an x-intercept and a y-intercept. The other thing you might notice is that you've got a division here, and you're not allowed to divide by 0. So actually there's a vertical asymptote here. Because you can't divide by 0, when the bottom 0, so that's when x is minus 1, that can't be part of our domain. That's where our vertical asymptote is going to occur. So we've got a vertical asymptote happening at minus 1. So on our graph so far, that would mean we've got a y-intercept of minus 1, an x x-intercept of +1 and a vertical asymptote at -1. So we'll draw that as a dashed line. So that's a line that the graph is going to approach, but it's not going to touch. So here's our vertical asymptote. Now that's not much to go by on to draw a graph. There's another feature that we can find, and that's a horizontal asymptote. These will be easier to find once you have done more work on limits, but we can still talk about it. So to work out a horizontal asymptote, what we're doing is we're trying to find what happens to the y value when x is really big, when x approaches, I guess, plus or minus infinity, and our graph is x minus 1 on x plus 1. So when x is really big, or really big and negative, we want to know about how big is this number. And you can kind of estimate that. If you put a million in there, a million minus 1 divided by a million plus 1, well, the minus 1 and the plus 1 are really tiny compared to the a million. So it's about a million on a million, which is 1, right? And it turns out that is our horizontal asymptote. To technically work out this limit, though, a good way to do it is to divide top and bottom, every term on the top and bottom, by the highest power of x. That's x to the 1 here. So x divided by x is 1. 1 divided by x, well, that's just 1 over x. And on the bottom here we have x divided by x is 1 plus 1 divided by x. Now when x is really large, or really large and negative, 1 divided by a huge number is practically 0. So this approaches 1 minus 0 on 1 plus 0, and that's 1. So our horizontal asymptote, when x is huge, y gets really close to 1, so y equals 1 is actually our horizontal asymptote. So on our graph here, this is quite tricky to draw. We have a horizontal asymptote at 1. Okay, so what's happening with this graph is it's a hyperbola. It passes through this y-intercept and this x-intercept, and it approaches this vertical asymptote x equals minus 1, and it approaches this horizontal asymptote y equals 1. Now over on this side, what's happening is it's still approaching those asymptotes, but it's this branch of the hyperbola here. Okay. Now, one way we could see that that was actually a hyperbola without doing all this work here is to go back to this equation and do a little bit of a trick. X minus 1 on x plus 1. Well, actually, that's x plus 1 on x plus 1 minus 2 on x plus 1. Let me change the question, because x plus 1 minus 2 is just x minus 1, okay? But x plus 1 over x plus 1 is 1, so this is actually 1 minus 2 on x plus 1. And if you have an equation that looks like this, you can tell it's a hyperbola. It's just been transformed, it's being shifted a bit. It's being shifted left 1, right, across minus 1. It's being shifted up 1. That makes sense, because our asymptotes have shifted left 1 and up 1, and because it's minus 2 on x plus 1, it's actually these branches of the hyperbola as opposed to those ones. So if you can see a neat trick like that, you can transform the hyperbola and graph it this way. Otherwise, we can still sketch the hyperbola, we just need to find the x and y intercepts, the vertical asymptote, and the horizontal asymptote. So that's question 2. Question 3. So question 3 gives us a function, but it's a split function. It has 2 different rules for different domains. It's saying when x is less than or equal to 2, use this rule, 3x minus 4. When x is bigger than 2, use this rule, 8 minus 2x. So we're asked to evaluate some function values as well as sketch the function. So f of 0, we've got to work out which rule to use. Since 0 is less than or equal to 2, we're going to use our top rule here, 3x minus 4. So f of 0 is going to be 3 lots of 0 minus 4. That's minus 4. When we're calculating f of 2, when x is less than or equal to 2, so that's still the top rule here, 3x minus 4. So when x equals 2, we're going to get 3 lots of 2 minus 4. That's 6 minus 4, which is 2. Now, when x is 4, so f of 4, we're going to use the second rule here because 4 is bigger than 2. So 8 minus 2x is our rule. So f of 4 is 8 minus 2 lots of 4. Well, 8 minus 8, that's 0. So we've just evaluated the function at particular values 0, 2, and 4. Now we're asked to sketch the function. So these values should be on our sketch and we'll make sure that that's true. When we want to sketch the function, essentially we want to sketch y equals 3x minus 4, but only take this section when x is less than or equal to 2. And we want to sketch 8 minus 2x, but we only want to take the section when x is bigger than 2. So if I was sketching 3x minus 4, if I was sketching y equals 3x minus 4, then that's a straight line. It's a straight line with a gradient of 3 and a y-intercept of minus 4. So I can sketch that, or you could find some x and y intercepts and join those up. 3x minus 4 would go through minus 4, and it would go a gradient of 3, so 3 up for every 1 across. Would be 3 up for every 1 across. 3 up for every 1 across. So here's our graph of what y equals 3x minus 4 looks like. It's actually got an x-intercept of 4/3, and we could work that out by solving y equals 0. Oops. I'm just drawing it dashed here because, so this is y equals 3x minus 4. But we only want to take that graph when x is less than or equal to 2. So when x is equal to 2, we know f of 2 is 2. We know that from part 1 anyway. And we want to take it for x less than or equal to 2. So x is less than or equal to 2 is all of this side. So we want this straight line down here. Now, I'm just going to go over it in black because that's going to be our answer. So the orange is the whole graph, but for our answer, we only want to take the section that's less than or equal to 2. I've coloured this in with a big dot because that's included. We want when x is 2, y is equal to 2. So that makes sense because f of 0 is minus 4 and f of 2 is 2, and I've coloured in that dot there. By the way, this x-intercept is 4/3 there. That's the intercept. Okay, now for the other side, we want 8 minus 2x, but we only want the section when x is bigger than 2. So what does 8 minus 2x look like? Well, it's got a y-intercept of 8 and a gradient of minus 2, or y-intercept of 8 and an x-intercept of 4. That helps. So our graph is going to come down here, this straight line. So this is the graph 8 minus 2x with a y-intercept of 8 and a gradient of minus 2, or an x-intercept of 4, so you can just join the 8 and the 4. But we only want to take that graph for x larger than 2. So we only want to take it from this side onwards. Now, 2 isn't on that function value. If 2, when you put x equals 2 in here, you do get 4. So it would have gone through 4, except we're not going to include it. And then we want to take this section when x is bigger than 2. Okay, and now this makes sense because f of 4 is 0, and f of 4 is 0, it does pass through So we've evaluated some function values and we've sketched the function by sketching this straight line but only taking the section less than or equal to 2, and sketching this straight line but only taking the section greater than 2. And so that's our sketch here. Maybe I'll just write in black that the black graph is y equals f of x. The last question on this class test was an equation. We want to find all real numbers such that the absolute value of 2 minus 3x is less than 3. Now, if the absolute value of something is less than 3, that means it must be somewhere between minus 3 and 3. There's lots of ways to solve these equations. I think this is one of the easiest ones, but you do have to understand what absolute value is. So if you want to absolute value a number, it's going to end up being positive. If you want that positive number to be less than 3, then originally it had to be wedged between minus 3 and 3. So 2 minus 3x is wedged between minus 3 and 3. So if we subtract 2 from every side, then we're going to get minus 3x is between minus 5 and 1. So what we've done there is we've subtracted 2. And now if we divide by minus 3, we just have to be a little bit careful, because when we divide by a negative, we're going to have to flip those signs. So when we divide by minus 3, we'll get minus 1/3 here, and we'll get minus 5/3 here. So this reads minus 5/3 is greater than x, which is greater than minus 1/3. That's kind of written a funny way around, because minus 1/3 is less than minus 5/3, and on the left of the number, on the number line, than this one. So we'd normally write it this way around, but that doesn't matter. So x is between minus 1/3 and minus 5/3. Now that's our answer, but we could write our answer using set notation. X is in this interval from minus 1/3 to minus 5/3. Doesn't include minus 1/3, so it's a round bracket all the way up to 5/3, and that's a round bracket there. Now they don't ask us to graph it on a number line, but we could. If they asked us to graph that, we would be saying that we want all the numbers in between these 2 points, but because we don't want to include the endpoints, we have open discs, open circles there. So this is the real number line. So that's the solution to the last question of this paper.